All right, good afternoon, everyone. Hope everyone had a good lunch. As a message from our sponsor, I've been asked to remind you in this and all the other sessions, don't forget to rate them on the app. It's a very short little survey, and it really helps the organizers and the speakers hone the content for next year. This session, as you've probably guessed, is continuous delivery for architects. I'm doing an entire continuous delivery workshop tomorrow, and it's all about these engineering practices that make up continuous delivery, which is really kind of an umbrella marketing term for effective engineering techniques for projects. It just sounds better if you call it continuous delivery than the longer, more cumbersome effective engineering techniques. And there are a lot of those. But this talk is really more about how the role of architect and the practices of continuous delivery intersect with one another. And they actually intersect with one another in quite a lot of different ways, which I'll investigate during the course of this talk. This talk is really in three parts. The first one of the tricky things anytime that you talk about or write about architecture is there are a lot of context that you have to have in place before you can understand the really important, meaty parts of what you're talking about. And so the first part of this talk covers some related concepts that are not purely about architecture, but closely related and, in fact, illuminate different parts of architecture, including some metrics and some ideas from domain-driven design. Then I talk quite a bit about building component-based architectures. This is part of the advice from the Continuous Delivery book, but it doesn't really get much more specific than build component-based architectures. In the real world, there's a strong differentiation between things like libraries and frameworks and things like service-based architecture, so I talk about practices around both of those styles, and in fact spend a bit of time talking about microservice architectures because they embody a bunch of the engineering practices that I'm talking about here. And then finally, I discuss some evolutionary strategies because I suspect many of you, like many people out in the world, are stuck with a kind of monolithic architecture right now that you're not completely thrilled with, and you'd love to move to a more modular component and or services-based architecture. So I give you some evolution strategies by which you can make that happen. So, having said that, let's first start talking about some concepts that overlap both these areas of continuous delivery and architecture. The first of these that I want to talk about is, there was a session here earlier this week I noticed, I think there was a workshop about this as well, this idea of domain-driven design, which is ostensibly an object modeling kind of exercise and technique to help you learn exactly what the partitions of your problem domain are and build what they call or what is conceptually in their world components. But the concept that we really strongly borrow from domain-driven design is this idea of a bounded context. I should probably go back and talk about these two books for a second before I do that. The Domain-Driven Design book by Eric Evans is the book that introduced this concept to the world. It is very abstract and a tad on the dry side. It's a little textbooky, kind of like the Gang of Four book. Von Vernon's Implementing Domain-Driven Design is a really good practical application of that stuff, so that's why I have both of those up there. But the idea that we're really borrowing from domain-driven design is this idea within domain-driven design of a bounded context. So in domain-driven design, when you identify a domain object, like a customer, it exists in a bounded context where that bounded context knows every single detail about what constitutes a customer, and nobody outside that bounded context knows anything about the internal details of it. They can ask it questions about customer stuff, but there's no internal intimate detail, so all the implementation details are encapsulated inside that bounded context. Now, in the domain-driven design world, that's a logical kind of separation, but this is a really important thing to make a physical separation as well in this continuous delivery world, because we'll see in a lot of services, and particularly microservice-based architectures, we treat the physical component boundary as a bounded context, never letting anybody outside of it understand implementation details like persistence mechanism or even what sort of format the persistence is in. It may not even be relational data. It could be some sort of graph database or something like that. But that's completely invisible to the outside world because each of those components or services act as a bounded context. The next concept that you have to be familiar with in this talk, of course, are the ideas in continuous delivery by Jez Humble and Dave Farley. Really, the focus of this book are good engineering practices that you can apply on projects, not even necessarily agile projects, because these are engineering practices. You can actually apply these to just about any project. And like I said, there are a good number of engineering practices here that you can rely on, but several of these engineering practices really impact the architect role a lot. And one of the things that you do in the continuous delivery world is create this deployment pipeline concept. It's kind of like continuous integration on steroids, because whereas continuous integration is kind of a bucket where you can do some stuff, run some tests and, run some metrics and other things like that, a deployment pipeline has multiple stages, and each stage does some sort of verification, whether it be running a test or some sort of, scalability verification or some sort of feedback that you want as you're trying to automate the build of your code all the way out to production. Ultimately, you build out this deployment pipeline idea. And that's important for the architect because you're going to be the one to set up this deployment pipeline. And there's not a known good set of, you have to have these three stages in your deployment pipeline. Every one of them is going to be different. And each one of these deployment pipeline stages, or whatever you end up naming them, can pass artifacts from one stage to the next stage because you're building up a release. The ideal here in the perfect world in continuous delivery is that you can also do continuous deployment. So you have this automated gauntlet of tests and other kinds of verification tools that run every time you check in code, and the ultimate outcome of that may in fact be going directly to production if you're in a continuous deployment kind of world. And so you're building up these assets as you go along. It's important here as the architect to understand what the purpose of having these pipeline stages is for. Your overarching goal here is increasing confidence in production readiness of your code. And so pipeline stages in a deployment pipeline become feedback opportunities. So any time in your build that you need feedback, that's when you create a pipeline stage to handle that level of feedback for you. So it may not even be a major thing. I was on a project not too long ago that had gotten burned in the past from having duplicate IDs in a internationalization translation file. And so they had a pipeline stage that made sure there were no duplicates in any of those files. It took about 2 seconds to run, so it wasn't a big dramatic thing, but it was something they wanted to make sure was in place before they moved on to the rest of the build. And so pipeline stages in this world become feedback opportunities. There's one other really important thing here for architects, and that is in this deployment pipeline you will reach a certain milestone within that deployment pipeline. In the continuous delivery book they call it the user acceptance testing stage, but that's just arbitrary choice on their part. You get to decide exactly when this magic stage is, but here's the characteristic that makes it this magic special stage. Notice that in the acceptance stage in this diagram, one of the first steps here is to configure environment. What that means from a continuous delivery standpoint is at this stage, we're going to start programmatically building out the physical environment that this code runs on. So if this is a Java project that runs on Apache with Tomcat, on CentOS version whatever, then delivery book, they call it user acceptance testing stage, but that's just arbitrary choice on their part. You get to decide exactly when this magic stage is. But here's the characteristic that makes it this magic special stage. Notice that in the acceptance stage in this diagram, one of the first steps here is to configure environment. What that means from a continuous delivery standpoint is at this stage, we're going to start programmatically building out the physical environment that this code runs on. So if this is a Java project that runs on Apache with Tomcat, on CentOS version whatever, then we're going to read a Puppet or Chef manifest file at this point of the build and build up a CentOS box and then install Apache and Tomcat, all that stuff on it, and then deploy our binaries onto it, and then run tests and other sorts of things. You'll notice that once you start doing this configure environment stage, you keep doing that on all the downstream stages. This is really operationalizing your architecture. And this is really important for architects because in the previous kinds of worlds, even in a lot of agile projects, architects didn't really worry about this operational business until very, very late in the project, until they really had to get the rubber meets the road and actually get it live somewhere. And there are a lot of hiccups that end up happening there. This is one of the problems. Anytime you delay some sort of engineering practice, this is one of the big lessons and the extreme programming guys gave us, and we later rediscovered in continuous delivery, that there are lots and lots of problems in the software world that the longer you put them off, the worse they get. And they don't just get worse linearly, they get worse exponentially. It has to do with the combinatorial explosion of how software pieces move against one another. And so a lot of the solution to pain in software is do things as eagerly as possible rather than put them off as long as possible. And this is exactly the motivation for doing this. If there are chances you're going to have weird interactions with your production, either operating system combination or topology or something like that, the faster you can get it into that realistic environment, the faster you will catch and resolve those bugs, and they'll be a lot cheaper to handle. So this is going to, so what that means is the architect has to be much more plugged in with operations and DevOps in this world much earlier in the project, because you're going to want to start building these pipeline stages really early on, and you need to handle all the details of what it takes to actually get this stuff to run in your realistic production environment. All the things in the continuous delivery book mostly assume a monolithic application, but what we really want to do is get the trigger of change to be as small as possible. And if we can start triggering change on a change in a component or a library and have that trigger the entire build pipeline, then that's a nice evolutionary step. And so that's one of our goals, is to get to the point where we can actually trigger change at the component level and have it automatically build out the application for us. Another observation here is one that I made in my keynote yesterday, or the day before, whatever it was. And that is that very often in architecture, yesterday's best practice is tomorrow's anti-pattern. We keep building architectures that solve outdated problems, because very often, one of the points I made yesterday is that architecture is by definition the stuff that's hard to change later when you build something. And if you build an architecture around particular constraints, when those constraints disappear, you still have those constraints modeled in your architecture. And we see that a lot in the architectures that we've been designing over the past decade or so, because there's been a lot of emphasis on being really effective at sharing resources, because we've always been chasing scalability. We always need more and more resources, and so there's been a lot of effort on how can we effectively share a bunch of resources. So we do thread pools and application servers and enterprise service buses and message queues and all those kind of architectures. The problem with that, though, is that those are really pretty architectures when you draw them on whiteboards and put them in Visio and talk about them amongst your developer friends. But until you actually put it in production, it's really abstract. Any kind of architecture is abstract until it's operationalized. And that's one of the things that the continuous delivery world has made us realize, is that you really need to think about the practical implications of your architecture very early on. Otherwise, you end up building big problems for yourself that could have been avoided otherwise. We've been spending a lot of time over the last few years building really good shared resources style architectures, so we can have monolithic application servers and run lots of things on those servers, and then cluster those things together when we need more scalability out of them. But just like other kinds of limitations in our world, the constraint that we build around has slowly disappeared, because shared resources is not our big constraint right now. It's not our biggest architectural headache. Resources are, in fact, really easy to spin up because of virtualization now. You can build virtual machines on the fly. You can get cloud-based resources. You can get Amazon resources for pennies per minute to do things. The big problems we have now in a lot of our architectures is the coupling that all those shared resources have introduced. Because when you have shared resources, you have layered architectures. When you have a traditional model view controller layered architecture, you're sharing all those things across all the different domains inside your application. The problem with that is if the customer part of your application really needs to evolve more aggressively than the order and line item part of your application, it's hard to do that because we're all sharing the same kind of technical infrastructure in the shared layered infrastructure. So what that ends up doing is encouraging big bang style deployment, because we can't just change this one thing without the ripple effect changing this one, of course, changing that ripples effect out, and so before long you're rolling out the entire thing in big bangs. It makes upgrading things difficult, because if you have one thing that's shared across a bunch of your stack, you can't just upgrade one piece of your framework. Your ORM changes and you need to upgrade it, but some of your application is not compatible with a new version. Ultimately what this does is make change expensive. And that's really bad because we're not good enough at doing agile change in architecture. That's really probably our weakest point still in the software world, is being able to make architectural changes. And a lot of the focus in kind of the modern services and microservices style architectures is exactly about this, is making change a lot less expensive and a lot less risky. And I'm going to maintain here that if you have a really good microservices architecture, you greatly reduce the risk of release. This is one of the happy side effects of having a well-defined modular architecture, and I'll show you why that is as we go along. So while this is a perfectly nice thing on paper with an enterprise service bus and this kind of choreography or this orchestration style integration architecture, this is really bad from a lot of standpoints, from a continuous delivery standpoint, because it makes building a deployment pipeline really difficult. Because when you have something like an enterprise service bus, what you've done is taken the behavior in your application that really should be encapsulated inside a domain and smeared it across your architecture. And now if I need to change the customer service, but some of its routing and transformation is in the enterprise service bus, now I've got to change that thing too. And of course that thing is connected to everything else on Earth, so changes there ripple to other parts, and so you end up in these big bang deployments. It's hard to do domain-driven design. It makes evolutionary architecture difficult as well. So last of these kind of conceptual things I want to talk about is metrics and monitoring. We talk a lot about monitoring in the continuous delivery world because if you're going to be really aggressive about doing all this operational automation in the DevOps world, you need to make sure that you can monitor to make sure that inadvertent side effects are not popping up because of this. There are lots of really good writing in the book Release It by Mike Nygaard about setting up circuit breakers and other sorts of architectural patterns and operations to prevent bad things from happening. But a lot of those rely heavily on monitoring. I don't talk much about monitoring here because this is more of an architecture talk, so I want to talk about some metrics. And in fact, I want to talk about two metrics that are really, really useful to architects and some tooling that will help you use those metrics on projects. And the two metrics I want to talk about are actually the two, or close to the two that I talked about in my emergent design talk yesterday. One of them is cyclomatic complexity, and the other is the two-pair effort coupling. So cyclomatic complexity has been around for quite some time. It works for pretty much any structured programming language, so this doesn't work for something like Prolog or SQL, but for any structured language you can get good cyclomatic complexity metrics, which gives you the merit complexity of a function or method. Thomas McCabe created this formula, and it is this, edges minus nodes plus 2, where nodes are lines of code and edges are possible pathways through code. And so if you look at this little method, you can count up its edges and nodes and see that 4 minus 4 plus 2, the cyclomatic complexity of this little method is 2. It's really testing decision points and possible routes through your code to see how complicated it is. Here's a slightly more complicated function with its edges and nodes drawn out. The cyclomatic complexity of this guy is 3, so it's one more complicated than the one we saw before. Cyclomatic complexity is a useful metric because you can derive a lot of other cool metrics from it. My emergent design talk yesterday I showed using cyclomatic complexity per line of code as a kind of a rough correlation of the amount of complexity churn that you have in your project. You can also use cyclomatic complexity to go and find the most complicated function or method in your entire code base, and that's almost always interesting to see exactly what that is. In fact, one of the fun things that I had to do, one of the challenges you have a lot of times when you're doing architecture on any kind of agile or continuous delivery kind of project is you didn't really have the luxury to spend a lot of time up front understanding relationships between things. And so it's kind of like taking off in an ultralight airplane and converting it slowly into a 747 while you're in the air. So you need to be able to poke around and learn what's going on in this code base as it's afloat. And so one of the things you need to be able to do is go and learn the quality of the code base really quickly. And so one of my favorite things to do is take cyclomatic complexity and go find the 5 most complex methods in a code base, and then for each one of those try to discern how much of that's kind of accidental complexity because of messiness and churn and other stuff, or how much of that is really the core complexity of what's going on in this application. So that's cyclomatic complexity, and I'll show you some interesting uses for this guy in just a second. The other metric that we're interested in here is the effort coupling pair metrics. These are both coupling metrics, and these work for any kind of code artifact. So this can be a class, or it could be a package or namespace. The afferent coupling are the number of incoming connections to that artifact, And the effort connections are the number of outgoing. The effort coupling is the number of outgoing connections from that artifact. The easy mnemonic to remember this is that effort starts with an E, and that's also the first letter of the English word exit, and these are the outgoing connections, so that's the easy way to remember what that metric does. This is a really important metric for architects because we're always kind of in the tension between understanding coupling points between parts of our architectures. This becomes a really important deal if you're trying to break your architecture up. So let's say you have a monolithic architecture and you're trying to break it up. Before you can start breaking it up, you really need to understand the coupling characteristics of how the sub-pieces of this thing fit together. So that makes this a really, really useful metric. So let me talk about some uses for these and some tools around these. There are two typical uses for metrics on these kind of projects. Building information radiators that you wire into a continuous build, like continuous integration or deployment pipeline, something that just automatically runs every time, and you can put it in an obvious place so that the information kind of radiates out. People don't have to chase it. And the other are probes where you go learn specific things about a code base. So here are a couple examples of each of those. The first of these is produced by a free, all the tools I talked about are free except one. This is a freeware tool called Source Monitor, and this works on a variety of different kinds of code bases. So this works on C# and VB and Java and a bunch of other languages. And this is a common metrics visualization that some other tools produce as well, but this one produces a pretty nice version of it, called a Keynote graph. And the idea of the Keynote graph is for all these metrics, you set up what you believe are acceptable ranges that you will like for those metrics. So complexity here, when this tool talks about complexity, that's our friend cyclomatic complexity. So that's what I'm saying here is the average cyclomatic complexity can be between 2 and 4. The maximum cyclomatic complexity I want to be between 2 and 8. And so you can set up these ranges of acceptable values, and then you graph an actual class on top of it. If this were an ideal class from a metric standpoint, it would fall exactly into the middle of this donut of goodness. And the more it diverges from this nice circular shape, the odder this class is from a metric standpoint. And so you look for weird deviations here. And in fact, for any Java developers in the room, this is actually quite a common pattern in the Java world. Because you'll notice in this, for this particular class, this is a class in the structs code base, this particular class, its max complexity is really high, but its average is really low. What would cause that particular shape? And like I said, it's quite common in the Java world. This has to do with a particular quirk of the Java language in that there's no native property syntax in Java. Properties consist of pairs of getter and setter methods. And so when you see a class like this, what you're looking at is a class that has a whole bunch of getter and setter methods, which are very, very simple methods. But then there's also a rule in Java that has a very specific recipe for creating an equals and a hash code method, and those can be quite long if you have a lot of fields. And so that's a really common pattern because you have two gigantic methods that's making your max higher than the threshold, but you have so many tiny methods that's pulling your average below the threshold. That's a pattern that you don't typically see in a language like C#, which has native property syntax. It's just quirk of Java and the way that methods are reported as properties in Java. My colleague Eric Durnenberg has got a lot of really interesting visualizations on top of existing tools, and that's his website. He's actually working on a book now on visualizations in software metrics world. There's a common metrics tool in the Java world called checkstyle. It's very similar to a tool in the .NET world like FXCop and one in the Ruby world called RubyFoo that runs a whole bunch of different metrics around different criteria. The criteria here that checkstyle uses are things like Boolean expression complexity and cyclomatic complexity and nested expression depth and a statement length and complexity, etc. And so what Eric did was take the output of checkstyle, which is normally XML, massaged it through a little Ruby script into comma separated values, and then pull that into Excel and graphed it so that you can see a graphical representation of the kind of bad parts of this code base, and you can easily narrow in on these classes as being the problem children in this code base because they have a cumulative bad score. This is another graph that I showed yesterday, and I won't spend much time on it now because I talked about it quite a bit in my emergent design talk. This is another visualization created by Eric, and this one shows churn on a code base and some efforts that were taken at this point to kind of calm things down and clear out technical debt. And he used this visualization as the evidence that we need to do something because we have a lot of churn and cyclomatic complexity. and then use this as evidence that they were in fact making progress toward their goal. This is a really important thing in the continuous delivery world, because what we're really after in the continuous delivery world is to make software like engineering. And one of the things that the characteristic of engineering is repeatability. You need to be able to do things and be able to measure them and repeat them. And so we're really big about making hypotheses and then trying experiments to see if we're making things better or worse. And this is the kind of thing that we use to track to see if we're doing better or worse. So those are some radiators and some visualizations. Now I just want to talk about a couple of probes. This is a tool that was inspired by an old school Smalltalk tool. Smalltalk was really some of the first guys to really do object-oriented programming at an industrial scale. And they invented a bunch of really cool metrics tools. They invented so many metrics tools, in fact, that they created a meta platform for metric stuff called Moose, like the animal moose. And even today, if you have Java or Python or PHP or C#, if you can get a tool that will convert it into Moose metadata, you can use all these old school Smalltalk tools because they all talk to this particular metadata format. There's an old school tool called Code Crawler that you can do this with, but there's a modern version that's written for Java that works as an Eclipse plugin. So here's a code base in X-Ray, which is the modern version of this. We're looking at an entire code base here, and those are inheritance relationships. In fact, I'll show you what those look like. What we're looking at here is inheritance relationships of the lines. The length of the box is the number of lines of code, and the width of the box is the number of methods in that particular class. And we can zoom in on one piece of it here and see a little more detail. So here's more detail about this section right here that's zoomed in. So you can zoom in and out. But just by looking at this, what does that tell you about a class like this guy? Really long, not very wide. So lots of code, not many methods in it, which is a little bit smelly. I might be curious to see exactly what's going on there. But here you can see the inheritance relationship. So this is kind of a different way of looking at your code base. But the real value in X-Ray comes not from this view. Well, actually, there's a nice thing about this view in that once you click on one of these classes, it will show you its after and efferent coupling. And the stronger the weight line, the more connections there are between those two things. So you can see a very faint pink lines here. Those are skew connections, and these are deeper connections, and the arrow indicates whether it's afferent or efferent in going incoming or out. So that's kind of an interesting view, but an even more useful view in X-Ray is taking all of a particular thing and looking at its dependencies together. And so here are the package dependencies for a particular project. And again, the weight of the line here indicates the strength of the coupling between those things. And so now you can see that several of these classes are very highly coupled together, and some of the other ones are not very coupled at all. This is the package view, package and namespace view. You can also drill this down to the class view, and this is the class view of that same project. And you can actually see a lot of similarities between the package stuff and the class stuff. It lays it out in the same order. You can see some of the same hotspots in that version. This is an open source project, Argo UML, that is an open source UML modeling tool. It's a really pretty good size, a swing-based desktop application kind of thing. And this is its class level coupling in X-Ray, which is really bad. One of the nice things about X-Ray is you can actually turn down the volume and say any of the connections that are slower than a certain threshold, then don't show them to me so you can get rid of some of the noise. And here's the package stuff for Argo. Again, pretty complex. And you can click on any of these guys and get the actual details of the package, namespace, or class, or whatever it happens to be. So that's that one. So that's the idea behind X-Ray, and in particular these extra views. These extra views in X-Ray. You can actually use this. I'll show you how to use this in an analysis capacity a little bit later on when you start thinking about breaking it up in monolithic architecture. So that's X-Ray, and by extension, the tool Code Crawler, which can be used on a variety of different code bases. The last one I'll talk about very briefly, because it's kind of cool. Again, inspired by an old school Smalltalk tool. This is an implementation that works against Java code bases. What this does is take your code base and convert it into a three-dimensional city that you can sort of fly through, as if you're in a helicopter or an airplane. So this is Code City, this is our code base. The same rule applies here. The length is the number of lines of code, and the width is the number of methods. That's the straight down as if from an airplane view. But you can also turn on some things here. It'd be kind of a cool little visualization. You can just see the pretty picture. But you can also turn on some colors here that are illustrative. What I flipped on there were God classes and brain classes. A God class or a God object is a well-known anti-pattern. It's an object that knows too much or does too much. These are classes that have really high effort and effort coupling. They know too much or probably do too much. What kind of classes do you think normally have really high effort and effort coupling and it's kind of okay? Controllers, workflow, because they gather up model objects and make them do stuff, and then they forward stuff over to views. And so if you turn on God objects and things other than controllers light up, then you may have too much responsibility in some of your domain classes. The brain class is one that has really high psychometric complexity. It has a lot of complexity and therefore it is brainy. And so you can turn on the threshold for that too and see which one of the classes are particularly complex. The other cool thing is will let you do are snapshots over time. It won't automatically do snapshots. You have to tell it I want a snapshot, but you can do snapshots over time. These are packages and namespaces in the neighborhood right here. So you can see this code base slowly growing over time. But I want to go back for a second to this weird little neighborhood right here that wasn't there, and it was there. So what is that? What is this neighborhood that popped up all of a sudden? Remember the characteristics of the things in Code City and in X-Ray. The really tall things have lots of lines of code, and the width indicates the number of methods. So this whole neighborhood of little spindly things popped up all of a sudden. Anybody have any idea what those things are? This is another common pattern. Code generation. They typically get generated in their own package and namespace structure, which you see this entire package name structure pop up. And when code generators typically build very few methods and build lots and lots of very long code because they're just generating big piles of code. So if you're the architect on a project and all of a sudden this weird neighborhood pops up, you might want to go investigate exactly why that's going on, particularly if you didn't realize that anybody was doing code generation on your project. So those are really nice uses of metrics on projects, and we'd like to leverage metrics even more, but there are some really serious limitations to metrics in the software world. One is the signal and noise problem. A lot of times there'll be a useful kind of information in a metric's trying to tell you, but there are other really noisy metrics around it that are drowning out the usefulness, and so you can't really tell what's useful or not. The other problem we have is we have no one true metric that really tells us a lot of deep things about our code bases. We don't have anywhere near the rigor that traditional engineers have, because we haven't been working at it for as many thousands of years as they have. Even really useful metrics like psychometric complexity, it cannot differentiate between essential and accidental complexity. All it can do is identify complexity, and it takes an extra person reading the tea leaves to realize should that be there, or is that something that's been added as an artificial artifact. The problem with metrics is they're gathered but ignored. You wire this into an automatic build and then forget about it, and a year later you go, oh yeah, we've been producing metrics for last year, and it says our code sucks, and it's too late to do anything about it. Inaction and overaction are both equally dangerous. Inaction for obvious reasons, because you wire these things up and don't pay any attention to them. But overaction can also be a problem here, because of something that I highlighted in my keynote yesterday, that very often meta work is more interesting than work. If you get a bunch of developers really, really excited about a metric, they will start gaming that metric to the point of insanity. And they'll start doing really stupid things just to game the metric, because that becomes their new meta work goal, is to make this metric perfect and then maybe build some software along the way of optimizing this metric. And so you have to be careful that you don't get people too excited about this and have some governors on that. And very often in this world, you prefer trims to discrete values, because again, one of the limitations in metrics is that the raw value may not tell you much. Psychometric complexity, for example. You have a method that has a psychometric complexity of 12. Is that good or bad? I don't know. It depends on what the essential complexity is. But if it's 12 today, and I check it again in a month and it's 20, and I check it in another month and it's 55, clearly it's going in a bad direction, and we should see if there's some way we can break that up. Even if it's essential complexity, maybe we can modularize it or break it into smaller pieces so we can logic it out more effectively. Sonar is a really nice free tool in the Java world, and it gives you a lot of really nice graphs and trends and other sorts of things like that. And this, in a lot of ways, is the really usefulness of metrics to demonstrate some case that you're trying to make, and trim lines and animations, things like that, make that a much easier case to make. Okay. Next, I want to talk about component-based architectures. And there's a chapter in the Continuous Delivery book that gives some advice about component-based architectures, but doesn't really pull apart the real differences much between libraries and services. This is the advice from the Continuous Delivery book. Use components to decouple parts of your application and change at different rates. It turns out this is only one of the decisioning criteria. Is how do you decide how to partition things in services, but this is a really good one. We need, though, to make a further distinction about components here, because component is too generic a term. We want to further differentiate this into the idea of libraries and services. Libraries run typically within a single process and communicate through language function call mechanisms. So these are internal coupling. These are things that you compile into your application. These are compile time dependencies. So these are the libraries you use. These are the jar files in the Java world, the DLLs, the .NET world, the gems in the Ruby world, all compile time dependencies. Whereas services tend to run in a separate process and communicate via integration architecture formats like HTTP or TCP/IP, or higher level things like REST or SOAP or something like that. So let's talk about each of these things in turn, because most modern systems are going to consist of both of these kinds of components. Even if you have a services-based system, each of your service will still have a bunch of frameworks and other libraries that it encapsulates within it. So let's talk about some practices around each of these things individually. And let's talk about libraries first. So let's say that you decide, rather than building a monolithic application every time, you want to break it into a smaller set of components, libraries, and frameworks. So we have our portfolio management application. We have a framework, which everything is based on. Then we have the reports engine, the settlement engine, the pricing engine. They all rely on framework, and those all feed into the portfolio management application. And let's say we have this third-party library guy here that we get from some site through a Maven repository or NuGet repository or something like that, something that we're integrating into our code base. One of the first things we have to worry about here is managing dependencies. And most people's first real encounter with how much of a headache this could be is the phenomenon that we used to call DLL hell in Windows. But the reason I bring it up here, do you remember DLL hell, I'm suspecting? The System32 directory where they shared all those libraries and new applications, put newer versions in and break old applications? Why did that exist? Why did this problem exist? It's exactly the problem we're fighting right now because of shared resources. When Windows came out, hard drives weren't big enough to statically link all those applications together, so they made an architectural decision in Windows to make most of it work through dynamic link libraries. By the time most of us encountered DLL hell, we had plenty big enough hard drives, but this problem persisted at least a decade past when the constraint that forced it to be there had already expired. This in a nutshell is what we do in architecture all the time, is build around constraints, and that constraint melts away, and all we're left with are the constraints we put around ourselves. Today, though, we basically have two approaches to handling this. You have some sort of ubiquitous live directory in your project that has all the things that make up your project, and anybody can add stuff to that live directory, but nobody ever removes anything from that directory, because you're terrified that it might accidentally destroy the earth if you did that. I'll show you a tool in the Java world that can show you how you can remove stuff if you don't want them anymore. But everybody always ends up in a transitive dependency management tool. In the Java world, it's Maven and Ivy. In the .NET world, it's NuGet. In the Ruby world, it's Bundler. It's a pip and Fabric in the Python world. You always end up with this because this is just a hard problem to solve. And so you always end up with tooling to manage this for you. One of the problems that come in when you have libraries like this are circular dependencies. This is when you have something that depends on something else that eventually relies back on the thing at the top. This is particularly aggravated by modern IDEs, languages like Java, and to a lesser extent Visual Studio and C#, because the tooling is being too kind to you here. Because you're typing along in your Java IDE and you reference some class that is conceptually 1,000 miles away, what does your IDE do? Your IDE says, oh, you don't have that imported yet. Would you like me to auto-input that for you? And as a developer, you swat that dialogue away so fast now that you don't even realize it came up. If somebody asks you after the fact, did you auto-import something? You'd be like, no, I haven't auto-imported anything today, because you just did it. It's a reflex now. Same happens in all these IDEs. What you really need is some sort of little clipping mechanism in your IDE that pops up and says, should you be importing this thing? Because you may be making a real mess of the dependencies in your project and creating cycles in your code base, but that doesn't happen in any of these modern tools. The IDE is trying to be as convenient as possible, but sometimes convenience is not necessarily the right thing to do. And having cycles in your code base makes the system really, really hard to componentize, and it makes your life cycle a lot more complex than it has to be. So let me show you some tooling. This is a nice little tool in the Java world, a little open source tool that's been around for a long time, but I talked to Kurt not too long ago, bumped into him. He said this is probably still the most downloaded thing from his website, this jar analyzer. What you can do with this jar analyzer is take a directory full of jar files and run the jar analyzer over it, and it will show you how they're all connected to one another. And it produces a nice report that has actor and effort coupling and all these other nice metrics in there. But the really valuable thing it produces, it uses GraphViz to produce a drawing to the relationship between all the pieces of your system. So this, for example, is for Struts 1.0, the web framework. But in the Java world in particular, if you ignore this problem, it can get really, really out of hand. Because this is the diagram for Struts 1, and here's the diagram for Struts 2. Yikes. That's terrifying. But this is what happens if you just let anything couple to anything else anytime you want. You end up with a spider web and this nest of connections between things, and it's really, really hard to start untangling that if you need to start untangling this to build some sort of less monolithic architecture. This is the only commercial tool that I talk about in this talk because it does a really, really good job of doing this. This is particularly for Java, this tool Structure 101. It analyzes your code base and gives you a to-do list of refactorings that allows developers to go in and untangle cycles. Through the .NET ecosystem, there's another commercial tool that does a similar job called Independ. That's also quite nice. It doesn't give you this to-do list thing, but it does show you where things are connected to one another. It also gives you a nice matrix of how connected things are to one another, so you can start doing some analysis and start pulling things apart if you want to. And so it's useful to go in and use a tool like this to go in and untangle those cycles and get your code base in a much more nice componentized way. Once you have those things untangled, though, you want to make sure that you don't accidentally retangle them. And so here's a nice little way to do that, particularly in the Java world. There's a metrics tool in the Java world called JDepend. It's been around for quite some time, and it is itself written in Java, and it does actor and effort coupling for packages and classes in the Java world. But because it's written in Java, you can actually have it do some analysis for you, and so once you've gone into your code base and painstakingly removed all the cycles that are there, go in with JDepend and write this as a simple unit test for your project. Because what this does is go look at all the packages you have in your system, and then will return true if you have cycles or not. So you can set up a failing unit test in case you accidentally introduce a cycle. A failing unit test will keep you from checking into the code base and go fix it before you have to go and untangle it at some point later down the road. Independ also has a mode where you can use it to run as a checking mechanism like this, not as part of a unit test, but as a tool so that you can check and wire up the same kind of automatic mechanism to do a safety check for you. And in fact, Independ is even more powerful than that because with, JDepend is a very similar tool. JDepend is free and Java-based. Independ is commercial and .NET-based. The other cool thing you can do with JDepend is go in and tell it what kind of relationship you'd like to have between your packages. Because a lot of times you'd like to have a one-way relationship between two packages. Let's say you have a web package and a util package. It's okay for web to import from util, but you never want util to import from web. So you want that kind of one-way relationship in some cases. You can go in JDepend and tell it, add all the packages you're interested in, and then give it rules about how they should depend on one another, and then run this dependency match, and if you violate any of these rules, then it will fail that test. This is exactly the kind of thing that we like to set up on our projects. We don't like setting up scenarios where we have a bunch of really complex, arcane rules that developers are supposed to follow, and then you yell at them and punish them when they don't follow those rules. We'd much rather let people fall into success. So set up little automated checks and tests and other things so that if somebody accidentally does do the wrong thing, something catches it before it ends up getting into the code base and keeps it from escalating into this big problem. Where we're going with this, of course, is the ability to pipeline libraries together, so that if I make a single change to a library, that will trigger a change that will ultimately rebuild my application and build it out to a deployable kind of artifact. So here's another problem we have. We have a component-based system, diamond dependencies. Here's how this manifests. So let's say that you have this set up, and you've made a change to framework, and you run all of its tests, and everything's cool. Everything's fine with framework. Because it has updated itself, it's going to try to automatically update its downstream components. And so reports engine tries to run its test, and everything's cool in reports engine. But when pricing engine tries to incorporate that change, it cannot for whatever reason. Something breaks, some unit test breaks, some sort of incompatibility is there. Now the $64,000 question is, which version of framework should the portfolio management application rely on? And of course the answer is none of the above. There's no legal version for it to rely on because two of its upstream dependencies have different dependencies themselves. This is a kind of a headachy problem in the wild world where you don't control the build order of things, but for your components and your libraries, you can solve this problem with your deployment pipeline. You just have to make sure that all dependencies get resolved before they go to the next stage. So the way you would set this up with your deployment pipeline is have framework here. A change in it triggers a build in pricing engine, settlement engine, and reports engine, but only if all three of these are successful does it then promote and try to do a build for the application itself. So resolve all dependencies before moving to the next level of downstream dependencies, then you have to worry about this diamond dependency problem popping up. So that's all stuff about components and frameworks and libraries. Let's shift over and talk about service-based kind of systems now. And kind of service-oriented architectures, but a kind of a modern approach to service-oriented architecture. In the next few slides, I'm going to do what is common in the Agile Manifesto is prefer the thing on the left and the thing on the right, which is not to say the thing on the right has no value. We just prefer the thing on the left for some reason. And this is one of those. When we're doing this kind of integration architecture, we tend to prefer choreography to orchestration. Let me explain what I mean by that. In traditional kind of service-oriented architectures, in the enterprise service bus kind of architectural pattern, you have this enterprise service bus that handles things like transformations between two services and handles routing and logic around getting services to communicate with one another. That's the traditional kind of enterprise service bus pattern. And this is an orchestration style of integration architecture because the enterprise service bus is sort of like the conductor of an orchestra. Anytime somebody has to do something, they check with the conductor to make sure it's okay for them to do that, and they can continue on. We prefer choreography. In a choreography style in integration architecture, individual services communicate with other services to decide what they should pass back and forth and have no third-party guy involved whatsoever. And so in this world, teams just get into a discussion and decide on a case-by-case basis, what do you need from me? Okay, what do you need from me? Okay, let's start passing that stuff back and forth. One of the side effects of the kind of enterprise service bus, service-oriented architecture kind of structure is that you will accrue a pack of enterprise architects around this enterprise service bus, just like barnacles gather on the bottom of ships in the ocean because of this phenomenon called Conway's Law, which I'll talk about in just a second. It almost dictates that not only will you get a bunch of enterprise architects here, but they will start arbitrating what things are allowed on the enterprise service bus, and they will start being a governor to the rate of change for the services they deal with, because now they become a bottleneck to deployment to make changes to those services. In the choreography world, though, each one of these services is allowed to evolve at its own natural rate if it wants to. But that sounds kind of dangerous, because now we have these ad hoc relationships between services, and we're letting them evolve in any way they want to. How can we ensure that they don't break some existing assumption that they're already integrating with? There's a really common engineering practice here that's referred to as consumer-driven contracts. So the idea here is that when I want to enter a relationship with another service, I enter into a consumer-driven contract with them. So let's say that this guy is the service provider and this guy is the service consumer. What's going to happen is these guys are going to hand these guys a set of unit tests. And these guys promise to run those unit tests every single time they make a change to their code. That set of unit tests encapsulates what this team needs from that service. And now this service can evolve in any way that it wants as long as it doesn't break those unit tests, because those unit tests encapsulate their understanding of how those two things are going to integrate with one another. This is this idea of consumer-driven contracts where you have one team, you have a lot of other teams that, that need that service. They can connect to that and create contracts between those guys. So in this scenario, this particular development team is running 3 different sets of unit tests on behalf of the people that are integrating with him. And I promise to keep all those unit tests green every time I do a build. That means that this service over here is allowed to change in ways that doesn't break those unit tests. And if they do need to break those unit tests for some reason, that becomes the placeholder for conversation. If I need to make a change that's going to break the unit test for these guys, members of these teams need to get together and update the contract between the two of them, and now they can continue working again. This is a really nice safety net that allows you to have more or less independent evolution of speed of features, but still have some certainty that you're not breaking existing integration assumptions. Another one of these preferred things is we tend to prefer REST over SOAP. And here's why. SOAP was modeled as a remote procedure call mechanism. So that works really nicely when you have 2 parameters that match up exactly on both sides, which is exactly what you're expected to here. The problem, of course, comes when things evolve over time, and then you have to start doing versioning and stuff like that. And so because it is at its heart a remote procedure call kind of mechanism, it creates really brittle endpoints. If any parameter changes, then you have to rebuild the endpoint, and that's really brittle. We don't like that level of a forced change. This is one of the reasons that we prefer REST, because REST, because it's trying to model resources rather than trying to model remote procedure call endpoints, resources tend to evolve naturally over time and additively over time. And so if I'm asking for a particular resource now, and that resource additively changes over time, it doesn't change the resource that I'm asking for, because I'm just asking for the same subset I was asking for before. Then I don't have to do any kind of rebinding at endpoints or anything like that. And in fact, REST can even be more forgiving about slight version differences and variations, things like that. And so ultimately, REST is less brittle at integration points. And in integration architecture, you don't want brittleness, because integration architecture is about how things work against one another. And the more brittleness you introduce there, then the more likely you're going to get breakages. If you can build some bendable joints with your integration architecture, then you tend to break things a little less aggressively. So let's talk for a minute about service-based architectures, but really microservice-based architectures, which in many ways is kind of service-oriented architecture done right. I talk about and contrast the kind of traditional SOA with the microservices stuff. So the things I want to talk about here apply certainly to service-based architectures, but particularly to microservice-based ones. And the reason this is so interesting in this particular topic is because this microservice architecture style is the first post-DevOps revolution architecture. It's the first architecture that kind of fully embraces all the operational concerns from the operations world into the architecture itself. All future architectures will have to do this. This just happens to be the first one to take on that extra burden. So let's talk about some characteristics of microservice architectures. And this goes back to some of the stuff I was talking about before, of shared resources versus individual systems. So in the monolithic world, you tend to build big industrial machines and then run multiple things on machines so you can share resources on those machines. In the microservice kind of world, each service runs in its own process and in its own either logical or physical machine. So it acts as its own process. In the monolith world, the way you scale these things is to take monoliths and then cluster them together to build clusters of monoliths. Whereas in the microservices world, if you need more scalability, you split up more versions of the same service, so you can have multiple versions of the same service running and scale across those as you need to. It's a very process version of scaling versus a threading version of scaling. So very closely related to the way Linux tends to work by scaling the processes rather than threads. I mentioned Conway's Law before. Here's the formal definition, and this is surprisingly powerful in this world. Melvin Conway came up with this law about 20 years ago, I think. It's this observation that any organization that designs systems ends up producing a design that copies the organization's communication structure. What this suggests is if you have UI specialists and middleware specialists and DBAs running around in specialized roles, then you're going to end up with a layered architecture. This is kind of inevitable that your architecture will start looking like the communication structure between the silos that you've established in your organization. Here's a cartoon reprinted by request, and it's actually funny, but it's also accurate. Because Amazon created this concept. So we've known since about 1975 what the optimum size for a software development team is. Between 8 and 12 people. Fred Brooks identified that in Mythical Man Month, and he did this by looking at an analysis of more than about 10 people on a software project, and the communication overhead starts being more than 50% of the time you spend on the project. And so there's an optimal sweet spot number. And so Amazon a few years ago read that and really took it to heart and created this concept that they call 2 pizza teams. No team in Amazon is larger than can be fed with 2 large pizzas. So from a practical standpoint, it's 12-person maximum. But to do that, they had to create these really cross-functional teams. So every team has an operations person, has business analysts, and has a product owner, it has developers, has business analysts. Everything required to manage and operationalize that service is part of it. This is also kind of accurate about Google, because Google doesn't like dependencies. Google loves statically compiled languages and manages all dependencies at compile time. So they love big, fat executables where they never have to resolve any kind of dependencies at runtime, and so their structure tends to look kind of like that. I think this one's kind of funny too, the Oracle one with the legal department and the engineering department. So this is actually surprisingly accurate, but what we're saying here is that what Conway's Law ends up saying is you end up structuring your development teams like this. And that's not good, because now what you're trying to do is have this communication structure build a services-based architecture, and so it's harder to do that. What we're suggesting is what we're calling the inverse Conway maneuver, which is exactly what Amazon did, and that is to take these people and instead create cross-functional teams around the problem domains that they're working in. So have an operations person, a QA person, a business analyst, and developer on this cross-functional team and become better and better experts at the domain that they're working in all the time. Another one of those perspectives that comes to us a la Amazon is products versus projects. Because one of the kind of anti-pattern things out in the world is you get a group of developers together working on a project, and they work on the project until it hits the completion date, whatever that means. Which means that they put it into production, they pass that code over to someone in operations, and then that team gets disbanded and reformed somewhere else and start working on another project. And this guy in operations has to do the care and feeding of this project for the rest of its life. And very often you can't get things changed in that project. If it's got a memory leak or something like that, it's hard to get the old team back together to fix it or do bug fixes or anything like that. Amazon flipped this around. Said projects are evil. We want to build products instead. From this perspective of Amazon, their attitude is you build it, you own it, and you run it in production, and if something crashes, then somebody on your team gets paged at 3 a.m. in the morning to fix it. So these cross-functional teams own every single aspect, including the operations of the services they create. And every one of these products have a product owner who owns this product and advocates for its reuse amongst other product owners within the Amazon ecosystem. So rather than just abandon this project, you stay with this product forever. You keep building enhancements to it, and you sell it within the organization as a better and better version of that same product. There's a weird, interesting side effect at work here as well. particularly around Conway's Law. Let's say you're in a big, giant organization, and some code that you wrote a couple of years ago blew up in somebody's face in production overnight, and you come in the next day and you get this email that says, yeah, this thing you worked on a couple of years ago, somebody had to get up in the middle of the night and fix that, and it's like, wow, man, that must really suck to be him. Let's see if I can go create another disaster here. The problem is there's no connection to that person. That's just some person in a silo somewhere that got really massively inconvenienced. But if somebody on your team was paged at 3 a.m. in the morning last night because of something that you screwed up on, and you have to sit across from them at breakfast the next morning, you will become a better developer. Because you don't want to look in their face. When you got them up at 3 a.m., it's like, dude, I am sorry. It's no longer this anonymous thing in a silo somewhere. It's part of your team. It makes you a better developer if you really care about the operationability of your code and what it really does in the real world, not some sort of abstraction from a test center. Another characteristic of these architectures tend to be smart endpoints and dumb pipes. So I spent a little while ranting like a madman a little earlier about things like enterprise service buses. It turns out if you have an enterprise service bus and you never use any of the routing or the transformation stuff and just use it as a dumb pipe, then we're okay with it. What we're looking for is not smearing any of the domain stuff out into your integration architecture. If you're just using your enterprise service bus as a transport mechanism, then it's okay, because now it's just plumbing, and we don't have to touch it when we touch parts of our domain. So our goal for these services is to be as decoupled and cohesive as possible, inspired by the way that Unix pipes and filters work, where they all take in a consistent format and all output a consistent format. The transport for these things tends to be HTTP when we get away with it, because of course it's nice and it's easy to read into and easy to debug. But if you need performance, we will do things like messaging over a lightweight bus of some kind and go through some sort of binary protocol. Another feature of these architectures tends to be decentralized data management. Things like transactions are really, really easy when you have a monolith. And this is a problem for us because we often sell our users transactions as if they were a free thing. And in some architectures, they look like they're free. When you have a client-server system or a big monolithic system, then transactional boundaries are pretty easy. When you start splitting things out into services, transactions get a lot trickier because most of these services operate on this idea of that domain-driven design concept of a bounded context. And so if you have a customer service, its bounded context is going to include its persistence mechanism, which means whatever data data store that you're putting stuff in. Now you've got a real problem if you have transactions across these guys. And so it's very characteristic in this world for these kinds of systems to be eventual consistency or base kind of system versus transactional systems. This is perhaps, if you're in the position of untangling a monolith and trying to build a more services-based system, this is going to be one of the biggest headaches you run into, of where are the transactional boundaries in the existing system. And in fact, that may be the first place you go look for as a way to carve it apart, is preserve the existing transactional boundaries first as an easy way to kind of piece things together and then start attacking those as a smaller and smaller pieces. But this is one of those things, I talked about this in my keynote, that we sold our users that transactions are free, and they're not. They actually have a really, really high architectural cost. And this is one of those things that, I'm sorry that we sold this to you as free, but it turns out that to meet some of the goals that you're going to want to meet down the road, we're going to have to give up some of this kind of transactionability. Now, having said that, and the whole world kind of eventually goes to eventual consistency, there are still some situations where you need transactional kind of behavior. If you're selling airplane seats and there's a lot of contention and you just have a few left, you need real transactional behavior. And so it's not uncommon in this world to compromise a little bit on the architectural purity of the system and say, you know what, these two services know each other's details about their persistence and they need to share transactions across these two services. And that's not a war trying to do that as long as you go into that with open eyes and realize that you're doing this for pragmatic purposes. In other words, don't invent some crazily elaborate mechanism just so you can have the purity of having these isolated services. There's nothing wrong with a little bit of sharing there as long as you know what you're doing. One of the nice benefits of this, though, is that we now get decentralized governance. One of the tricky things when you have enterprise architectures and you have these big shared resources kind of architectures is it makes the decisioning for enterprise architects really, really difficult. Because they can't just pick the ORM tool that's going to be perfect for this small project. They have to think about every project's use of object relational mapping. And so what you tend to get are really big industrial strength generic things so that everybody can use them all equally. But things that are generic are by definition not optimized for particular problems. But in this world where everything is a bounded context, you don't have to make that decision for everybody. So let's say that these guys in the customer service decide, you know what, we're only going to ever have 2,000 customers ever. And we never have to do any kind of sophisticated query or anything like that. And this team is now responsible for operationalizing their data store because it's part of their bounded context. They're going to have, as part of their build up the database programmatically. I happen to know from experience that you can take a raw IP address and install Linux and Mongo on it and have it up and running in about 90 seconds flat. And I'm pretty sure you cannot get the first install dialog for Oracle to come up in just 90 seconds. And so maybe this team decides, you know what, we're not going to use Oracle in this project because that's like going rabbit hunting with a bazooka. We just need a little bit of persistence here, and we'll manage that ourselves, and we're good, and you make a decision, and then 6 months later it's like, oh, man, that was a terrible decision. That is just not working out. We need to change that for some other open source solution. You change it within your bounded context, and nobody else ever realizes that happened. Because nobody else is coupled to your implementation detail. What this means is that every team gets to pick the kind of technology that makes the most sense for the project they're working on. A lot of dysfunction gets driven into large companies because you force every developer to use the same very generic industrial strength tools and databases and languages and all that stuff, where some projects are very small and simple and could get done in a fraction of the amount of time if they picked a more suitable technology for solving that problem. Now, there are a lot of complications in the style of architecture. Let's talk about some of the advantages of going to all the extra effort to do all this engineering to make this possible. And here's an example of the advantages of having this style of architecture. Let's say that you have a really good microservices-based architecture running out in your ecosystem. This is a typical kind of thing to do in a microservices kind of world. So you need to build a UI here for a user. So a user makes a request to your website. When they make that request, it spins off to a whole bunch of services and their clock starts ticking. Some of those services start sending back results, and those get queued up to be aggregated when we're finally going to build the display. So multiple services are coming back, and some take longer than others. And at some point, you decide, okay, time's up. We need to render a display, and now you render a display with the information that has come back to you. Some of these other services will still send you stuff back, but it's too late. I've already rendered my UI. Maybe next time you'll be fast enough to get your result into this UI, but I had to, when the clock ran out, I need to render my UI. So in this kind of world, you actually prefer timely partial results to slow complete results. Because the slow complete results didn't make it and get rendered because they take too long to get there. And so you could have a situation where I need to give a weather report, and I can give you a really rough weather report in like 200 nanoseconds, and I can give you a really good one in a second and a half. It may be that you have a clock set that says, I'm perfectly good with a rough weather report because I need it back a lot faster, but maybe in some cases I need a more complete one, and I'm willing to wait longer to get the more complete weather report. The other observation here is that the return here is optimized for ranking and aggregation and not display. So all the display characteristics that belong to the UI, it's gathering up mostly JSON data feeds and then aggregating and ranking them so that it can produce a result when it needs to. When you have a lot of services running like this and can run at scale, you can do some really cool stuff. Here's an example. So have you ever wondered how Google does that kind of magical, did you really mean this when you misspell something? Here's one way that this could work. When you issue a query into Google, it doesn't issue a single request to a search engine. What it does is take that request and permutate it in common misspelling ways like transposing letters So when you make a Google search, you're actually spinning off 200 or 300 different requests. And if one of those come back with like a 92% match correlation, and the others come back with like a 6% match correlation, Google will say, did you really mean this instead of that trash that you typed in? Because I got really good returns on this search, and I got really terrible search results on this other thing, so I think you probably meant this. The reason they can do that is because they can operate at scale, because they can spin off a few hundred requests for every single time a user makes a request, and still come back as fast as they do. They're running a clock just like that. They just have a really fast clock because their services run really, really fast to do this stuff. That's the kind of thing that you do when you operate at that kind of scale. There's a common practice in the continuous release world of canary releasing, doing a slightly different version of something for some part of your users. Google routinely canaries off 1% of their users to test new search algorithms. And what they do is you'll get a new search algorithm, and then other people are doing the same search term. They look to see, did you click on a higher link on the page than people who are using the old search algorithm? This may have been a better search algorithm for you. So they do a bunch of what-if analysis, those kind of things, because they can operate this kind of scale. So one of the observations in this world is to standardize on integration and not on platform. You don't really need to force everybody to use the same language here. In fact, it's a bad idea to force everybody to use the same language because there is no single one true language to rule them all. Now, we're not suggesting that you go completely crazy here and let every team pick whatever language they want. But if you look at most organizations and look at the spectrum of too few languages to platforms and too many languages to platforms, most organizations fall firmly on the too few rather than the too many spectrum. My colleague Sam Newman has written a book about microservices, and one of his pieces of advice is standardizing the gaps between services and be flexible with what happens inside the boxes. So in other words, it's perfectly okay in your ecosystem if you have some people doing Java development and some people doing .NET and some doing Go. Google's Go language is really popular right now for building these microservices because it's a very simple language, has very few dependencies, so it makes a good platform for building these kind of services. But like I say, standardize on integration, not platform, but don't go completely crazy. So have 1, 2, or maybe 3 ways of integrating, but not 20 different ways of integrating. And pick some sensible architectural conventions and try to stick with them across all of the services that you're creating. So let's talk for a second about deployment, because we're advocating here lots and lots of different languages. But what we don't want is a completely different deployment scenario for each one of these guys. That just makes the operationalized ability of this really, really cumbersome. And so we want to use mechanisms that make all of them look exactly the same way. So we'll use some sort of containerization kind of technology so that even if a Java thing, it gets deployed just like it was a Linux process, and if it's a Go thing, it gets packaged so that all of them act the same way when we put them in operations. And Sam's advice on this is abstract out the underlying platform differences to give you a uniform deployment mechanism. So don't focus on making everybody write in the same language, because the language really affects the way people think about the problem. Instead, standardize in the way you put things into production and let people choose the right language for the job. An observation about this kind of architecture is that microservice architectures promote coupling from application to integration architecture. Here's what I mean by that. If you look at application architecture, everything is cohesive inside there. All the coupling is inside it. These are all function calls, method calls within this monolithic application. When you split this out into a services or microservices-based architecture, though, now all those coupling points get written at the integration architecture level. And there are pros and cons both ways for this. Notice that these guys still have internal coupling because these are still applications that are pieces of this, but the main integration is between these core scripting services. So like I said, there are pros and cons here. The pros of doing this is it makes you really explicit about coupling dynamics. It's easy when you're working inside a monolith to just let anything call anything else without really thinking much about the relationship between those things. When it's in integration architecture, you have to think much more carefully about what kind of information is passing from this subsystem to this subsystem, because you have to formally model that in integration architecture. It forces coarser-grained coupling points. You can't be as chatty as you can with function and method calls if you do integration architecture. And it relies on engineering practices for safety. So you can't just go hog wild here and build a service-based system without having some sort of safety nets to make sure that things work the way you think they do. The cons here is exactly the same thing. Undisciplined coupling becomes a mess. If you just basically, this is the giant anti-pattern, the tools like Visual Studio, which will take any method and let you right-click on it and make a SOAP endpoint for it. And now, oh look, now we're integration architecture. And now the coupling is rampant and out of control, and you have terrible latency. You have to be very disciplined about this. And transactional boundaries become an architectural issue here, where they typically are not within application architecture. This starts becoming a much bigger deal when you get to integration architecture. So let's talk a little bit about a couple of deployment details and integration and disintegration. One of the bold claims I made earlier is that if you have a services or microservices style architecture, you can actually reduce the risk of your releases. And here's why that is. Let's say that you have your production system here. One of the things, the terms that I introduced in my keynote was this thing that the closure guys have resurrected, this archaic term called complex, which means to weave or braid together. One of the problems that we have in deployment is that deployment and release are currently complected together in most organizations. One of the things I wanted to simplify this is uncomplex those two things. I want to separate deployment from release. In fact, I want to do another level of decomplecting as well. So in this world, in this really mature continuous delivery kind of world, you have components, and components are deployed into the ecosystem. But the features that we're going to utilize inside those components are not alive yet. They're still turned off under feature toggles or a strangler pattern or branch by abstraction or one of the engineering techniques that we talked about in the continuous delivery world. At some point, once you've monitored and made sure that component is stable in the production ecosystem, then you turn on those features by flipping feature toggles or turning on the branch or branch by abstraction, or changing proxy server. Notice that in this world, it's perfectly okay to have another service that's almost identical to the current one. Maybe this is a new search algorithm. Maybe this is a new way to do ratings for videos or something like that that you're trying out on some subset of your users. No, there's no problem yet because we don't have applications yet. We just have features that are running. And in this world, applications consist of the routing between those services. So in this world, let's say that I roll out a brand new search algorithm. I deploy that component into the ecosystem and monitor to make sure everything's cool. Then I turn on that feature and monitor to make sure everything's cool. And now I want to try it out. I route over to it and something goes crazy. I reroute back to the original one. I don't have to redeploy anything. I don't have to roll back my entire deployment because applications consist of routing. And if a service starts misbehaving, you just route around it to another service that's not misbehaving. And you learn that by monitoring because you monitor all those services all the time. This greatly cuts down the risk of trying what-if games and having experiments in production because you can just roll stuff out and not worry about, as soon as you roll them out, having some impact on your users because you decouple the deployment from the release and from the actual people using whatever that feature is. One of the things we talk about in continuous delivery world is this idea of blue-green deployments where you have two identical production stacks, a blue slice and a green slice, and you switch back between them. This is typically done at the entire layer or infrastructure level. What we're talking about here is this blue-green capability for services. You deploy it, you release the feature, you route to it, and if something goes wrong, you reroute around it if it blows up. So this gets back to my contention that when you think about how big should your services be, this is one of the first questions you ask. If you have a monolith now and you want to go services, how far down this path should you go? The point of this is that if you have good engineering maturity, which may be a big if, the more services you have, you actually drive your risk of release lower and lower and lower. Because you have finer grained services and you have the ability to put them into and take them out of the ecosystem without hurting anything. When you have a monolith, you have a gigantic risk of release. Because if something goes wrong, then the whole world is messed up. Whereas in this world, the more services you have, you actually drive the risk down. Let's talk about integration for a second. So one of the things that we do in this world is monitor, and we monitor all the services to make sure that they're all running, and that they're healthy, and that they're doing the stuff that they're supposed to do. But what happens with services that nobody's really using anymore? One of the anti-patterns in the kind of service-oriented architecture world is people spin up services and put them somewhere, and then nobody ends up using them, and nobody ever gets rid of them. They just kind of lurk around forever, and you have this massive technical debt because you have 20 or 30 services that nobody's actually using, but you're afraid to decommission because you're not sure that everybody's using them. In this world, what we do is we monitor not only the services, but also the routes that we're using. Because in this world, the application consists of routing. This is something that was popularized by Netflix, which has one of these kinds of architectures. They run a regular sweep every month or so and look to see any service that hasn't been routed to in the last 3 months, they disintegrate it from the architecture, from the production system. Because nobody's using that anymore. They integrate things into production and they disintegrate things back out of production when no one's using them. So they have a kind of a garbage collection sweep every month or so from their production ecosystem to clean up all the services that nobody's using anymore. So they really have a kind of Darwinistic environment for services there. New services come along that displace old ones because they have new capabilities. More people start routing to the new one until the old one's not being used anymore, and it gradually just disintegrates as an operational concern by the DevOps group. One of the side effects of all this microservice stuff is you really have to be this tall before you can start doing microservices. You have to have really good, mature engineering practices before you even start down this path. One of my colleagues says, I think this is probably true, if you're deploying more than 3 services by hand, you've probably already lost. So microservice and service-based architectures are more complex than monolithic architectures, but they give you some capabilities that are very hard to achieve in monolithic architectures. Like the ability to play what-if games with individual behaviors in your system, and the ability to put things into and take things out of production without having negative impacts. Those are all really nice benefits of the style of architecture. So let's talk a little bit about evolutionary strategies. I was talking before about how big should you make these things. If you're going to break down a monolith with a bunch of services, and nobody can really tell you exactly what the right size is going to be. And I wouldn't start off by taking your monolith and trying to break it down into really super fine-grained microservice right away, unless your problem domain just kind of naturally falls in that structure. Remember the advice from earlier to standardize on integration, not platform. So what you're going to do is partition along natural boundaries that already exist in your architecture. Maybe those things are transactional. So maybe you have a system where you have 3 or 4 major transactional pieces. It's very easy to split that monolith into 4 big services and have the transaction boundaries inside those services. And only once you get that stabilized, you start thinking about taking those services and further breaking those down into smaller pieces. What you'll find is you'll get that transactional boundary to a smaller and smaller and smaller scope, which is really good from a usability and a scalability standpoint, because you're being forced to think about exactly where does this transaction boundary have to be for it to work correctly. Maybe, though, you split things along domain boundaries. So maybe you take one team that already knows a fair amount about the problem domain of customers or orders or legal or something like that. Or maybe you split it along natural boundaries like organizational boundaries. Some people are in one physical location versus another physical location, and so you may split along those lines. So the trick here is to find a balance between how big you want to split these things down and the way you want to structure teams and other sorts of things around the ecosystem of that service. Remember I showed you X-ray before? This is the X-ray diagram from an actual project that I was working on. Client's name withheld by request. But if you look at this and kind of blur your eyes like an impressionist painting, you can see some definite hotspots here in terms of things that are coupled. So right here is a definite big hotspot. There's another one here, and there's another one over here. I happen to know in this particular piece of code, this thing is HTTP session because what this code base was using session as a giant global data store. So what they were doing is they'd do some process on stuff and then fill in this data structure in HTTP session, and then the next piece of the process would pull some stuff out of there and add and put some more stuff in it. So they're basically using it as a giant global data store. And we're looking at how would you partition this out into the services-based architecture. And the piece up here, all of this coupling right here was really around one piece of that process. And so we really just kind of partitioned along the natural boundaries that were kind of already here. All of this interaction between HTTP session here was building up one part of the information they were trying to work on. This was another part of that information, that coupling with this class over here. And so we basically split those out into services and preserved the transactional boundaries along those stripes first, and then started looking at building those in smaller pieces. So some of these visualization tools, by showing you coupling hotspots, can help you find ways to break things down and reorganize things. One of the things that we're really big on in this world is a holistic approach to engineering practice. Everything interconnects on projects, so that goes back to what I was talking about before. As an architect, you have to think about all these things like tool choices and deployment pipelines and builds and all those sorts of things. And there's an important perspective here, and I think a lot of architects and operations people kind of miss. And it's that a lot of architects seem to think that they're trying to solve an equation. And they ever get these equations solved one time, everything will be perfect, and they can just step back and drop the whiteboard marker and walk out of the room and everything's done. But you're never solving an equation because it's always moving. It's always a snapshot of the process. Here's a little thought experiment for you. Let's say that I took a server. Let's say there's a Linux server. I built it up and installed a bunch of software on it. And then I unplugged it from the wall, unplugged it from the internet, and went and locked it in a closet for a year. And went and took it back out of the closet and plugged it back in. What's the first thing that would happen? 57 software updates available and 16 security patches, because even though I didn't touch anything on that machine, the entire universe kept moving beyond that machine. You cannot set up a machine and just think it's going to stay in that pristine shape forever. It's not an equation, it's a snapshot. And everything around it is in constant motion. That's why you have to automate all the stuff to build out machines. You can't just trust machine images because they always change. Even if you don't change them, the ecosystem in which they run changes without you. Because software doesn't age like fine wine or cheese, it rots, and it rots really fast. You have to stay on it all the time, and that's why you have to have all the engineering practices around automating machines and other stuff, because you have to stay on top of this. The more you put this off, the more painful it gets. So to conclude all this stuff, one of the goals here is to build architectures that support change to avoid this problem so that we don't keep chasing the same kind of anti-patterns over and over. I mentioned that we really like this idea of the inverse Conway maneuver. Build teams that look like the architecture you want, and that architecture will follow. I talked earlier today about efferent coupling being a really good metric for code artifacts, but it turns out it's a really good metric for your team as well. So strive for low effort coupling for your team if you're building cross-functional teams. And in fact, this is kind of the vision wrapped up in one big slide. You have these small cross-functional teams who have low effort coupling to one another, who have, anytime they integrate with one another, have consumer-driven contracts, so they have architectural safety, and they are putting stuff into production at more or less a natural speed for them, operationalized and automated as much as possible. So teams with low effort coupling deliver relatively independently into a common integration pipeline without fearing breaking each other's builds. That's kind of the vision that we're after here, and that's what we're building on these engineering practices for. That's all I have. I have probably time for one or two questions if anybody has questions about any of this stuff. Anybody? Yes, there's a question here in the middle.
What about, is there a danger of balkanization of lots of services in your company?
Probably, yes. So one of the things you need is a good service discovery mechanism. So there are several tools out there, like Apache Zookeeper is one of those. There's a tool called Pact.io that lets you do service discovery and binding. So that's the tools like Netflix, that's how they handle application consistent routing. So there is certainly a possibility of balkanization here. What we really want, though, is not really balkanization so much as specialization around domains. So So one of the benefits of having this kind of inverse Conway maneuver is when you have the customer team, they only really work on the customer domain, so they get really deep knowledge of customer domain, and they have some limited knowledge of the things they integrate with. So that's a little bit of balkanization, but I think not in a terrible way. So.
Maybe just a quick follow-on. If the service becomes very popular, so demand is high, and supply is many, then you are in the driving seat. So the contract building could be asymmetric, or very asymmetric at that moment.
Could be, yeah. But that's something you manage from a personal standpoint rather than a technical standpoint. Because you don't want that to become dysfunctional. But yeah, it's certainly possible. We've got time for one more question. Who's got the one last question? Who's got
Introducing new technologies into an organisation, as you're suggesting, and I suppose it's a variation of organisation issue that Chap Field's just asking about, but it can lead to a situation where you have the system and nobody understands the technologies used to deliver it.
Yeah, I wouldn't do that. I would make sure people understand what they're working on. But that's just professionalism.
That's because people leave.
You know, well, certainly they do, but you know what? You don't hire accountants and assume that they don't know anything about accounting. And you don't let accountants come in and build a brand new system without showing all the other accountants what they're doing. It's the exact same thing here. It's just professionalism. It's just part of what you do. And a lot of what we try to do is wire up engineering practices so that you don't have to have a person to tell you, oh, if you don't remember to hit that switch, every 4 hours and the world blows up. We don't try to set up anything like that. We'll have an automated process that is to switch every 4 hours to keep the world from blowing up. And if you end up doing something to break it, you can see that that's broken. So there are ways to mitigate this. But the flip side of that is, what if you never introduce new technology in your organization? It's going to be really safe and stable right until the day you've got a business because the competitors are beating you to death in the marketplace. So that's the risk of not introducing new technology in your organization. So there's a trade-off there between those two. You don't want to be crazily aggressive, but you have to be careful too. So I'll leave with this quote. William Gibson, the science fiction author, has a great quote that says, the future is already here, it's just not evenly distributed. And you look at companies that are doing continuous deployment right now, and you have to ask yourself, it takes a fair amount of engineering sophistication to do continuous deployment. Why are they going to the trouble of doing that? And the reason is, they're in hyper-competitive markets, where the amount of time it takes them to get a release out the door has become a competitive advantage or disadvantage. There's the innovator's dilemma. If you get an established kind of thing going with a big company or something like that, somebody can come along behind you and do something in a much more agile way and run rings around you and end up putting you out of business. That's the danger of not paying attention to this stuff. You can't just treat this like, oh, well, nothing is really changing the technology world very much. It's really in massive flux right now. And a lot of companies are going to get blindsided by this because all of a sudden they're going to have a competitor who can run rings around them in the marketplace, and it's going to be bad. So that's all the time I have. I'm 1 minute over, so thanks very much for coming. You do in the continuous delivery world is create this deployment pipeline concept. It's kind of like continuous integration on steroids, because whereas continuous integration is kind of a bucket where you can do some stuff, run some tests and, run some metrics and other things like that, a deployment pipeline has multiple stages, and each stage does some sort of verification, whether it be running a test or some sort of, scalability verification or some sort of feedback that you want as you're trying to automate the build of your code all the way out to production. Ultimately, you build out this deployment pipeline idea. And that's important for the architect because you're going to be the one to set up this deployment pipeline. And there's not a known good set of, you have to have these three stages in your deployment pipeline. Every one of them is going to be different. And each one of these deployment pipeline stages, or whatever you end up naming them, can pass artifacts from one stage to the next stage because you're building up a release. The ideal here in the perfect world in continuous delivery is that you can also do continuous deployment. So you have this automated gauntlet of tests and other kinds of verification tools that run every time you check in code, and the ultimate outcome of that may in fact be going directly to production if you're in a continuous deployment kind of world. And so you're building up these assets as you go along. It's important here as the architect to understand what the purpose of having these pipeline stages is for. Your overarching goal here is increasing confidence in production readiness of your code. And so pipeline stages in a deployment pipeline become feedback opportunities. So any time in your build that you need feedback, that's when you create a pipeline stage to handle that level of feedback for you. So it may not even be a major thing. I was on a project not too long ago that had gotten burned in the past from having duplicate IDs in a internationalization translation file. And so they had a pipeline stage that made sure there were no duplicates in any of those files. It took about 2 seconds to run, so it wasn't a big dramatic thing, but it was something they wanted to make sure was in place before they moved on to the rest of the build. And so pipeline stages in this world become feedback opportunities. There's one other really important thing here for architects. And that is, in this deployment pipeline, you will reach a certain milestone within that deployment pipeline. In the continuous delivery book, they call it the user acceptance testing stage, but that's just arbitrary choice on their part. You get to decide exactly when this magic stage is. But here's the characteristic that makes it this magic special stage. Notice that in the acceptance stage in this diagram, one of the first steps here is to configure environment. What that means from a continuous delivery standpoint is at this stage, we're going to start programmatically building out the physical environment that this code runs on. So if this is a Java project that runs on Apache with Tomcat, on CentOS version whatever, then delivery book, they call it user acceptance testing stage, but that's just arbitrary choice on their part. You get to decide exactly when this magic stage is. But here's the characteristic that makes it this magic special stage. Notice that in the acceptance stage in this diagram, one of the first steps here is to configure environment. What that means from a continuous delivery standpoint is at this stage, we're going to start programmatically building out the physical environment that this code runs on. So if this is a Java project that runs on Apache with Tomcat, on CentOS version whatever, then we're going to read a Puppet or Chef manifest file at this point of the build and build up a CentOS box and then install Apache and Tomcat, all that stuff on it, and then deploy our binaries onto it. All right, good afternoon, everyone. Hope everyone had a good lunch. As a message from our sponsor, I've been asked to remind you in this and all the other sessions, don't forget to rate them on the app. It's a very short little survey, and it really helps the organizers and the speakers hone the content for next year. This session, as you've probably guessed, is continuous delivery for architects. I'm doing an entire continuous delivery workshop tomorrow, and it's all about these engineering practices that make up continuous delivery, which is really kind of an umbrella marketing term for effective engineering techniques for projects. It just sounds better if you call it continuous delivery than the longer, more cumbersome effective engineering techniques. And there are a lot of those. But this talk is really more about how the role of architect and the practices of continuous delivery intersect with one another. And they actually intersect with one another in quite a lot of different ways, which I'll investigate during the course of this talk. This talk is really in 3 parts. The first one of the tricky things anytime that you talk about or write about architecture is there are a lot of context that you have to have in place before you can understand the really important, meaty parts of what you're talking about. And so the first part of this talk covers some related concepts that are not purely about architecture, but closely related, and in fact, implementing domain-driven design is a really good practical application of that stuff, so that's why I have both of those up there. But the idea that we're really borrowing from domain-driven design is this idea within domain-driven design of a bounded context. So in domain-driven design, when you identify a domain object, like a customer, it exists in a bounded context where that bounded context knows every single detail about what constitutes a customer, and nobody outside that bounded context knows anything about the internal details of it. They can ask it questions about customer stuff, but there's no internal intimate detail, so all the implementation details are encapsulated inside that bounded context. Now, in the domain-driven design world, that's a logical kind of separation, but this is a really important thing to make a physical separation as well in this continuous delivery world, because we'll see in a lot of services, and particularly microservice-based architectures, we treat the physical component boundary as a bounded context, never letting anybody outside of it understand implementation details like persistence mechanism or even what sort of format the persistence is in. It may not even be relational data. It could be some sort of graph database or something like that. But that's completely invisible to the outside world because each of those components or services act as a bounded context. The next concept that you have to be familiar with in this talk, of course, are the ideas in continuous delivery by Jez Humble and Dave Farley. Really, the focus of this book are good engineering practices that you can apply on projects, not even necessarily agile projects, because these are engineering practices. You can actually apply these to just about any project. And like I said, there are a good number of engineering practices here that you can rely on, but several of these engineering practices really impact the architect role a lot. And one of the things that different parts of architecture, including some metrics and some ideas from domain-driven design. Then I talk quite a bit about building component-based architectures. This is part of the advice from the continuous delivery book, but it doesn't really get much more specific than build component-based architectures. In the real world, there's a strong differentiation between things like libraries and frameworks and things like service-based architecture, so I talk about practices around both of those styles, and in fact spend a bit of time talking about microservice architectures because they embody a bunch of the engineering practices that I'm talking about here. And then finally, I discuss some evolutionary strategies because I suspect many of you, like many people out in the world, are stuck with a kind of monolithic architecture right now that you're not completely thrilled with, and you'd love to move to a more modular component and or services-based architecture. So I give you some evolution strategies by which you can make that happen. So, having said that, let's first start talking about some concepts that overlap both these areas of continuous delivery and architecture. The first of these that I want to talk about is, there was a session here earlier this week I noticed, I think there was a workshop about this as well, this idea of domain-driven design, which is ostensibly an object modeling kind of exercise and technique to help you learn exactly what the partitions of your problem domain are and build what they call or what is conceptually in their world components. But the concept that we really strongly borrow from domain-driven design is this idea of a bounded context. I should probably go back and talk about these two books for a second before I do that. The domain-driven design book by Eric Evans is the book that introduced this concept to the world. It is very abstract and a tad on the dry side. It's a little textbooky, kind of like the Gang of Four book. Von Vernon